Hello all, welcome to the video lecture series for the subject operating system. Now I am going to explain you all about what is primitive CPU scheduling. Let me tell you what is primitive first. Basically, primitive is a process can interrupt the other process when it arrives with low burst time or else highest priority also you can mention. Compared to the existing process in run, that is where it is running in the CPU, right? We used to call it as a critical section and many other process, right? So now this is the example I have taken. The primitive primitive CPU scheduling is all about it can interrupt when it has a lowest burst time or else the highest priority, so that it can interrupt the current process which is already running inside the CPU, right? In non-primitive, once the process is taken a CPU, it will complete the task and it will not leave the CPU until it completes the task. But here it is reverse opposite. Whichever process arriving at the late time, also later it is arriving and some process is already running inside, it will compare the burst time and it will compare the priority and it will interrupt the current process which is running inside a CPU. So I will prove that with one example. So this is the example for the scheduling algorithm called SJF, that is shortest job first. Now here you can check it. I have taken the same example which I was explaining for non-primitive SJF, right? Same process and the same example I have taken. So now let's check one by one. Now I have drawn this particular Gantt chart based on primitive data structure, that is primitive scheduling, right? Now say for example, I told you here also, I was explaining in my previous video, whoever comes first will be treated first and the next process which is coming next will be interrupted whenever it finds a higher priority or else the burst time is very lower than the ones which is arrived and higher for the process which is already inside. Okay, let's see. Now here you can check it. Who arrives first here? Process 4. You can check it over here. Process 4 arrived first. How long this process 4 will run? That is a very big $1 million question here. Why? Because we are talking about, you are listening into primitive process of scheduling, right? So this P4 will run for only 1 second. Why? Because whenever you are comparing this particular, the next arrival time is P2 and its burst time is, see here, by the time when this P2 is coming inside, this P4 has been executed for 1 minute. You can check it over here, 0 to 1. At the time of 1, this fellow is entering, that is P2 is entering at the time of 1 and it is checking its burst time is 4. By the time this burst time is completing 1 minute, so it is 5, right? So it is 5. So which particular burst time is lower here? P2 burst time is 4, P4 burst time is 5. Absolutely P2. That is the reason you can check it. P2 is taking the CPU. Now P4 is going out. Now P2 is taking P4 will go and wait in the ready queue, right? Again, it will wait for the next turn, right? P2 is coming inside and how long it will execute? You can check it over here, right? It is executing for 2 minutes. Why? Because 2 seconds or minutes, whichever the units you can take it. Why? Because see here, it starts at 1 and it takes 2, 3. By the time of 3, who is coming inside? You can check it. By the time of 3, this process 1 is coming and its arrival time is 3 and its burst time, you can check it over here. Whenever the process 2 is already running inside, it completes its burst time for 2 minutes. It is already run and process 1 arrives at the second is 3. By the time it is checking, it was run for 2 seconds is over. 2 more is to be completed, but here P1 arrives at the burst time of 1 and 2. So which has the lowest burst time? That is shortest job first. So 1 is shorter than this particular P2. So it is P1 is interrupting this P2. I hope you understood now. Now P1 is interrupting and it is running for 1 minute. So now you can check it. P1 has been completed its task. Nothing left to run here. Okay, now P2 has to complete 2 more, and P3 has to complete 2, P4 has to complete 5, P5 has to complete 3. Let's check who is coming inside after P1. Now check it here, which job has lowest here. Now say for example, one more thing you need to check. See here, I am just pointing out. When P1 is completing his task and the timer exactly points at 4. Now listen, here there is an arrival time you can check. By the timer 4, all the process arrived. I hope you understand. When the timer is 4, all the process has been arrived. That means now we need to check only the bus time, right? Not the arrival time and the bus time where we was keep on doing that. You need to check only one thing. When some process is running for more than this arrival time, then stop comparing this arrival time and bus time, right? Why? Because you can check it. We did this P4, P2 and P1. So this is the last process we did this and it completes at 4. By this timer, all the process has been arrived. That's a point. So now we are going to calculate only this bus time. Now see here, this is over. P2 is 2, P3 is 2, P4 is 5 and P5 is 3. Now see here, P2 and P3 have the same bus time. Which particular process has to be executed? The process which has a minimum process ID. That means P2 and P3, which one is minimum process ID? P2. That is what happening here. Whenever you have a choice to choose if two processes arrived at the same or else it is pointing at the same bus time, then you need to go for minimum process ID. So process ID 2 is coming inside. It is taking the process for 2 minutes. You can check it over here because it's left only 2 minutes. After that, only 0 left. This is also completed. So process 2 takes the CPU. It runs from 4 to 6. Again, 2, 5, 3. So who is shorter here? Process 3 because the bus time is 2. So process 3 is coming inside. It is taking the CPU and it is running from 6 plus 2, that is 8. After that, who is coming inside? Process 4 is coming inside and it has a bus time of 5 and process 5 bus time of 3. So which one is shorter job here? Absolutely P5. So P5 is coming here. It takes the CPU from the timer at 8. 8 plus 3, that is 11. And finally, who is coming inside? Process number 4. So process 4 is coming inside and it is running for 5 minutes. So after process 4, nobody else is waiting here, right? So this is also 0 and this is also 0. Finally, this fellow is coming, that is process 4. So no other process is waiting. So it will take the complete CPU from 11. And what is the bus time for P4? 5. So 11 plus 5, totally 16. So this is how this particular Gantt chart has been drawn for primitive CPU scheduling. I hope you understand this process, right? So every time if you want to compare this, we need to have an arrival time as well as the bus time. Most importantly, if you rewind the video and check it, I was very particular about all the process arrived at same time. What is the solution? If some process has completed the task and all the process has been arrived on that particular timer, then we need to check only the bus time. So these two principles you need to follow, then you will understand how primitive and non-primitive is working, right? So now you can check it over here just for the understanding. Now process 4, I was telling how this process 4 is running and process 2 was running. These are all the running method of explanation I have already explained here. Now here, how to calculate the waiting time, that's a point. Why? Because you can see here, process 2 is running for 2 different time intervals. Process 1 is only one time. Process 4 is running in 2 different time intervals. So the formula should be very effective. We cannot use the previous algorithm formulas. So what is the main objective of this formula is to derive the effective waiting time. So total waiting time minus execution time minus arrival time. Okay. So what is the total waiting time for P4? I have taken P4 because it is waiting time. You can check it P4. If you take the P4, that will be a better understanding. P4 waiting time is not 0. Why? Because it is initially waiting. There is no waiting here because it comes at 0. After that, please check it. It is waiting for the second round to complete the task, right? And only after this particular process 5. That is, its waiting time is 11, right? In order to complete the next process to be, in order to complete the bus time for this remaining bus time for this P4, it is waiting for 11 minutes. So it starts exactly at 11. What is the execution time for this P4? Before this, what was the execution time? It execute for 0 to 1. That means how many minutes? How many seconds? Minutes or seconds? 1. So that is what here. And what is the arrival time for this P0? Absolutely. What is the arrival time for this P0? You can check this table. P4. P4 arrival time is 0. So that is what mentioned here. So what is the answer? 11 minus 1 minus 0, that is 10. Right? So the waiting time for this particular P4, here it is waiting for 10 seconds to start the next repetition, next time interval to complete the bus time, right? So I hope you understand how exactly it is working. Simultaneously, you can check all the values one by one. You can check it. Now I am going to just go through all this thing. P2, and what is P2 here? And it is waiting time for this P2. Total waiting time for this P2 is 4 minus arrival time. Execution time is execution time is 2 minus 1. So P2 arrival time is 1. You can check it over here. P2 arrival time is 1. So here there is a process, right? And total waiting for this P2 is 1. Accordingly, P1, P3 and P5. So after doing all these things, you need to calculate the average waiting time. That is the answer for all the other process. 10, 1 plus 0 plus 2 plus 6 divided by 5. Totally, it has a coverage of average waiting time is equal to 3.8 units, right? So this is how the primitive SJF scheduling is actually working. I hope you understand the video. Thank you.